This is multilayer and converged protocols. As you might guess from the name, multilayer protocols are ones that operate at multi-layers of the stack. Converged protocols, multilayer protocols, you usually see these in real-time voice, video applications. So just a quick review of the OSI model and the TCP/I model. Understand that multilayer protocols, again, when we're talking about this, we're talking about protocols that operate at multi-layers of the stack. And essentially, TCP/IP itself is a multi-layer protocol as well when referenced against the OSI model. There are some different pros and cons for using multi-layer protocols. On the upside, they provide a lot of flexibility and resiliency in complex networks. You see these used a lot for communications and in SCADA networks as well. They also provide multi-layer encapsulation, so you can encapsulate protocols within protocols and give you some flexibility to establish tunnels through networks or get around things or through devices like IDSs that you may not be able to get through with just the single protocol itself. As a result of that, you may consider this a con or maybe not, depending on who you are and what you're trying to do. These protocols can be used for covert communication channels, so you're hiding information in these protocols. You can easily bypass restrictions more easily bypass restrictions or filters with these protocols as well. And you can, of course, overstep logical boundaries like VLANs with them as well. They are used quite extensively in SCADA and ICS networks. A quick review here, these critical infrastructure devices traditionally use proprietary protocol. That's changed as you have operational technology and information technology, OT and IT merging. And now frequently the TCP/IP stack is used in these SCADA networks and for SCADA communications as well. This causes concern when we're talking about critical infrastructure that uses these protocols. All of the traditional security concerns related to TCP/IP, these multi-layer protocols, all are applicable in this world now that SCADA and ICS are using these more common protocols. DNP3, Distributed Network Protocol, this is a good example of a multi-layer protocol. This is frequently used in process automation systems. You see this a lot in water and wastewater and in electric companies as well. A lot of SCADA systems use this. And this is how the master station communicates with the remote terminal units out there in the field. So as you're passing information back and forth between your control center and your individual field elements, this is the protocol that's doing that communication. And it was really designed for reliability, didn't really have security baked in from the beginning of it. If you're looking for SCADA protection measures, just recognize the fact that a lot of the things that apply to traditional IT and security networks here with protocols and denial of service attacks, session hijacking, man in the middle, operating systems, because that notion of operational technology in SCADA systems are merging with information technology, all of those vulnerabilities that we deal with on the traditional security side of the house apply to now the SCADA networks. Whereas in the past, because it was all proprietary, closed systems, you didn't really have to worry about that, but now you do. Converged protocols. So this is a slightly different concept, but these are protocols that are designed to transmit voice, data, and video together as a stream. And so you have quality of service considerations with this, where if you're trying to have a voice conversation, you don't want it to stutter because of the dropouts on your network. You want that to be seamless, and so you have some notion of real-time nature of these protocols. And so you have quality of service, which allows you to say, okay, this converged protocol is carrying our voice, data, and video stream as a single channel. We want to prioritize that over somebody browsing the web, checking email, doing file sharing, downloading music, whatever the case may be. But you can do that with these converged protocols, and it makes it seamless. Because you've got these protocols now all riding over the same infrastructure, you don't have to have dedicated voice circuits, dedicated data lines, or dedicated video lines, like you did in the past with some of the older proprietary video teleconference systems. And then there's this notion of IP convergence, where we kind of just hit on that, but it's the notion that you've got all of these services now running over a single network, the internet, internet protocol-based networks, as opposed to having discrete, dedicated lines for it. MPLS, multi-protocol label switching. This concept was built to make routing more efficient and do point-to-point services through routed networks. And so what you have is this system that uses short labels, source and destination, as opposed to IP address of hop 1, hop 2, hop 3, hop 4, whatever the case may be. Well, what that results in is a overhead, or less overhead for the system, and a more effective, efficient, faster routing system. You can put any protocol over these MPLS networks. Because it does encapsulation, you're basically shielding that traffic from whatever MPLS doesn't really care about what it's carrying, so you can shove anything through that layer. And this operates somewhere between data and network layer. You frequently hear this referred to as layer 2.5 protocol, but that's what they're getting at here, is that it operates somewhere between the data link layer and the network layer, because of the technologies that it's using and how it's doing its routing to figure out where it's supposed to get traffic to and from. iSCSI and FCOE. So these are protocols primarily designed for high-performance storage. You probably will recognize SCSI, Small Computer System Interface. A lot of the high-performance drives, disk drives, use SCSI interfaces. So iSCSI is just a network implementation, network protocol implementation of SCSI. A lot of hard drives use this, can be accessed over the network. You frequently see this in storage area networks. And it's the low-cost alternative to the next one that we'll talk about, which is fiber channel over Ethernet. And this is, it uses Ethernet, operates at the Ethernet layer, but below TCP/IP, so it's not that high in the stack. It does require special adapters for you to use this, and because it's using just Ethernet, it's independent of any type of forwarding schemes or routing schemes there. So it's extremely high performance, very high speed over this protocol, but you have to have the dedicated hardware to support it, and that's why you usually only see this in high performance storage arrays. Voice over IP. So this is probably one of the more common converged protocols or multi-layer protocols, use of multi-layer protocols you see in voice applications or VoIP applications. There are two different kinds of VoIP. There's IP-centric and IP-enabled. IP-centric is where you have your system is entirely based on IP, and the only analog connection, if you will, is the trunk between your digital switch, your digital voice over IP switch, and the public switch telephone network, or PSTN. That's the only point at which it becomes converted to an analog signal and out on the plain old telephone system. Then you have IP-enabled. And IP-enabled voice over IP networks are simply the end terminal. So this is your phone, the phone on your desk, your handset, your mobile phone, whatever the case may be, is IP-based. Everything else from the switching, the trunking that connects into the main POT system, all of that is analog and traditional from that sense. There are two main VoIP protocols in use. There's H.323, which was proposed by the ITU, and a competing standard, SIP, Session Initiation Protocol, which was proposed by the IETF. Both of them implement voice over IP, have provisions for audio, video, and data signaling in them. Unfortunately, because they are two competing standards, they're not really compatible with each other. And so what we have now are systems that use SIP. You see this with like Asterisk servers or some of the open source servers, and then H323, which you'll see used by some proprietary vendor implementations as well. For H323, there are some standards that define what the terminal is. This is your telephone itself, and how it communicates with other telephones or terminals, how it communicates with the gateways, and it provides basically real-time two-way communication between a phone and a phone. Then there's this gateway device, and that's the interface between your voice over IP digital network and the public switch telephone network. So if you're dialing a landline or maybe potentially a cellular number, you'll go through the gateway to actually reach that number from your voice over IP line. Then there's the gatekeeper device. This is what does call management, forwarding, offers all the features like voicemail and everything else. All of that is maintained by the gatekeeper. And then you have a multi-point control unit, and this allows conferencing between gateways, between terminals in those gateways. So here's a graphical depiction of it. And you can see up here in this big box, you've got your H323 zone, which includes the terminals, the gatekeeper, the gateway, multi-point control unit. All of that is considered a zone, and it could be entirely self-contained if you just wanted to have a voice over IP implementation that was just a local phones, local extensions. The key is where it connects from the gateway here, and it connects either through the internet to other H323 zones or SIP, and it connects to the public switch telephone network through this gateway. So that gateway device is what allows your VoIP implementation to actually reach the outside world. There are different kinds of protocols in use with VoIP. You have real-time transmission protocol, or RTP. There's no quality of service guarantee on this, but it does handle point-to-point or one-to-many conferencing solutions. There's real-time transmission control protocol, which essentially adds the delivery mechanism on that to make sure that packets are reaching where they're intended to go and reassembled on the other side. And then there's this notion or this protocol called Secure Real-Time Transmission Protocol, or SRTP, which adds confidentiality, message authentication to the real-time transmission protocol. And the neat thing about this is that there's no effect of this security implementation on quality of service. So you don't have a corresponding degradation in speed or quality because you're adding security, the security features of this protocol on top of the RTP. There's another protocol, the ZRTP, or Zimmerman Real-Time Transmission Protocol. This is an interesting one because it handles key exchange. So similar to the way you might exchange keys in an SSL session, ZRTP does that for voice over IP as well. And so it transmits, it creates a set of keys and then transmits them over the data channel using SRTP. The keys are not visible to anybody other than the endpoints because it uses the Diffie-Hellman algorithm, and therefore you can't compromise the session keys. You can't break or at least intercept and then replay the key exchange. And because of that, there's also no key management. So you don't have to make sure that this device has a key, that device has a key, and there's no coordination there. So it's really easy and relatively low overhead to add this type of security to voice over IP using this protocol. There are several considerations from a security perspective. Because it's voice over IP or internet protocol, any IP threats that are out there with denial of service, route redirection, man in the middle of attacks, all of that stuff that can happen with IP-based networks, you have the same considerations for voice over IP. There are some voice over IP specific threats with eavesdropping, sniffing, things that you can do with ARP floods to redirect terminals to different, perhaps rogue terminals that are out there. You can capture packets of a voice over IP call, reassemble them, and then listen to the conversation after the fact. And then some additional ones just from a configuration standpoint with rogue DHCP servers or rogue TFTP servers. Every terminal that's out there in a voice over IP network can be configured one of two ways. You can hand jam all the settings into the terminal itself, IP address, gateway, all of that stuff, or you can set it up to use DHCP or TFTP to pull the configuration. Now, if you know anything about DHCP or TFTP protocols, it's a first come, first served protocol. So if I'm a telephone and I broadcast out to DHCP and I say, I'm looking for somebody to configure me, the first person that answers me, I will take. That could be the legitimate DHCP server, or it could be a rogue DHCP server that somebody set up. The first one to answer wins. And the same with TFTP. There's no guarantee that I'm actually talking to a legitimate TFTP server. So if I can intercept that request and send a configuration back through TFTP, that terminal won't know the difference.